Hello, my name is Ravindra and I am presenting my ME420 Individual Research Project titled Design and Hardware Validation of a Vision-Based Intelligent ADAS Controller. My project is supervised by Dr. D.H.S. Maitripala from the Department of Mechanical Engineering, and it focuses on improving real-time collision avoidance and lane keeping assistance systems in advanced driver assistance systems, or simply ADAS. Problem statement. ADAS technologies such as collision avoidance and lane keeping assistance are critical for enhancing vehicle safety and reducing accidents. However, current systems face significant limitations. One of the biggest challenges they face is real-time processing. Many of these systems rely on GPU-based architectures, which, while powerful, introduce inherent complexities. As seen in this diagram, GPUs use multiple processing cores managed by a work distributor, communicating through a global memory interface. This setup can lead to latency issues, making real-time decision-making difficult. Another major limitation of current ADAS solutions is their adaptability to environmental conditions. These systems often struggle with poor weather, low lighting, and unexpected obstacles. The graphs on this slide illustrate how rain conditions significantly impact the detection range of ADAS-equipped vehicles. As precipitation increases, the effective range of these systems drops dramatically. Additionally, the images at the bottom show how deep learning-based object detection performs inconsistently. At night, an object is successfully detected, but in some cases, even in clear daylight, detection fails. ADAS systems also face hardware inefficiencies. Many current implementations are computationally heavy and require high power consumption, making them less efficient for real-time decision making. My project addresses these challenges by combining vision-based object detection with FPGA-based hardware acceleration to achieve low latency and high efficiency ADAS functionality. Feasibility analysis. To ensure the feasibility of my proposed solution, I have analyzed three key aspects. Vision-based object detection. I am using YOLO, which is You Only Look Once, a state-of-the-art deep learning model for real-time object detection. YOLO is highly accurate and efficient, making it ideal for ADAS applications. FPGA-based hardware acceleration. FPGAs, or field programmable gate arrays, are well suited for real-time processing due to their parallel processing capabilities and low latency. Simulation and testing. I am using Kala, a high-fidelity open-source simulator, to create realistic driving scenarios for testing. Kala provides a flexible and scalable environment for validating ADAS algorithms. I am using established datasets like Kitty and Cityscapes for training and testing the object detection system. These datasets provide high-quality annotated images of road scenes, which are essential for developing robust ADAS algorithms. I have access to FPGA development boards and the necessary software tools for implementing and testing the ADAS controller. Open source libraries like TensorFlow and PyTorch, along with FPGA-specific tools like Xilinx Vivaldo Design, provide a robust framework for developing and deploying deep learning models on FPGAs. Timeline feasibility. Our project is mainly divided into 5 phases. Literature survey, selection and development of the vision-based intelligent semantic object detection technique or the method, setting up the automobile simulator for validating and testing the controller, development of the control algorithm required to process the evasive manuals, developing algorithms to generate control signals required for the actuation of brakes, accelerator or steering, implementation of the developed controller in FPGA, GPU hardware for hardware validation. And for the literature survey, selection and development of the vision-based semantic object detection technique, we have allocated 5 weeks, and 4 weeks for setting up the automobile simulator for validating and testing the controller, 8 weeks for the development of control algorithm required to process the evasion manuals, 6 weeks for developing the algorithms to generate control signals, 6 weeks for the implementation in FPGA or GPU for hardware validation, 4 weeks for preparation of the final report and or research paper. Shown here is the timeline related to phase 1 of our project. Here is a timeline related to phase 2. Shown here is the timeline related to phase 3. Shown here is the timeline related to phase 4. Shown here is the timeline related to phase 5 and end of the project. Knowledge gaps identified. Through my literature review and research, I have identified several key gaps in existing advanced driver assistance systems. Many ADAS solutions struggle in low light, fog or heavy rain conditions due to reliance on conventional vision-based techniques. Limited real-time processing capabilities. Traditional CPU-GPU-based ADAS can introduce processing delays, making real-time collision avoidance difficult at high speeds. Hardware constraints for onboard processing. Most commercial ADAS solutions rely on power-hungry GPUs, which are not optimized for low-power automotive applications. FPGAs are underutilized despite their potential for low latency, energy-efficient processing in embedded vehicle applications. To overcome these challenges, my project introduces a vision-based FPGA-accelerated ADAS controller with 3 key improvements. Instead of using traditional GPU-based ADAS, the project implements real-time processing on an FPGA. FPGA-based parallel processing allows for hardware-level acceleration, making the system more efficient for embedded vehicle applications. Uses deep learning-based object detection such as YOLO, trained on diverse datasets to improve performance under low light and adverse weather conditions. Custom-built control algorithms will improve collision avoidance and lane keeping assistance, ensuring adaptability in dynamic road conditions. Adopted innovative methods. To overcome the challenges in current ADAS systems, my project incorporates 3 key innovations: hardware-accelerated real-time processing, vision-based semantic object detection, and adaptive vehicle control strategy. Most ADAS systems today rely on CPUs or GPUs for processing, which can introduce latency and high power consumption. Instead, my project uses an FPGA-based implementation which provides parallel processing capability, real-time decision making, and power efficiency. Instead of traditional object detection, which only identifies objects without context, my system integrates semantic object detection to improve ADAS decision making. A key limitation in existing ADAS is the reliance on pre-programmed fixed responses. My project introduces an adaptive control strategy to improve safety, including dynamic evasive maneuvering, customized control algorithms, and scenario-based testing in Scala. I aim to develop a vision-based hardware-accelerated ADAS controller that overcomes the limitations of existing systems through a combination of real-time FPGA-based processing, vision-based semantic object detection to enhance scene understanding. I look forward to refining this approach further, testing it in simulations and implementing it on FPGA hardware. Thank you for your time, and I welcome any questions or feedback. Thank you.